Thank you very much for the invitation to talk at the conference. So I have to apologize first that maybe in the first 30 minutes there won't be any p-adic family of molecular forms, but they will show up at some point. So bear with me. So first I want to give a quick introduction to the Gross-Kohnen-Zagier theorem and really tell you what I mean by the Gross-Kohnen-Zagier theorem, because there are many different formulations. So, and I should also say this is all joint project, joint work with Léa Béniche, Henri Damon, and Mathieu Rosette. So let's start with the setup. So I start with B, Q, quaternion algebra. That's algebra which is indefinite. So you can think about the matrix algebra for the moment. And V will be the space of elements of trace 0. So JavaScript 0 means always trace 0 in my talk. And on that, I have the quadratic form given by the reduced norm. So this is a three-dimensional quadratic space of signature 1, 2, right? And so the units of B act on B via conjugation. And this gives me, well, the syntax clearly X-trivial. So this gives me an isomorphism between B cross the units in B modulo center to the special orthogonal group of this space B. Okay. So I like to consider the following conic. So I consider all lines in the vector space of B such that the quadratic form restricted to L is 0. So this is just the space of isotropic lines in B. This defines me a curve. And note that I said that my V is indefinite. So V handled with space change to R is just the 2x2 matrices of R of trace 0. Right? And so this CV is really just the conic is given by matrices of trace and determinant 0, so nilpotent matrices up to scalar. So I really get an isomorphism CVR with just D1 over R by mapping such a nilpotent matrix to the kernel or the image of the map. All right. And I mean, your B star locally at R is just two of R. And so this isomorphism here is compatible with this kind of isomorphism. I mean, you have an action of SOV clearly on here. Okay, great. And I want to consider the following symmetric space. So H, which is just the C-valued points of C without the C-valued points, the R-valued points are conic. So it's just by this isomorphism, you can think about like the upper and lower half plane. So really, what I want to do is introduce like classical Schmurk over Q, but everything in an orthogonal language, because this makes life later easier. Okay. Furthermore, I choose R to B Eichler order. And I mean, it's not important for the statement of the theorem I first give, but later in our approach, we somehow need a square-free level function. Okay. And then we can look at the Shimura curve attached to this level. So this will be some curve defined over Q. And C-valued points will be this H divided by the units of R. That's the kind of Shimura curve I want to consider. Shimura curve. And on this type of orthogonal Shimura curves, there are a lot of special divisors. Namely, we start with any V in V that has positive norm, the cube V positive. I can look at the divisor delta V with just those lines in H that are orthogonal given V. By this positivity assumption, you can see that this has consists of exactly 2 points. I mean, the orthogonal complement of V is, the thing you start with is of signature 1, 2, so the orthogonal complement is of signature 02. So it's definite over R. So there are no isotropic lines defined over R, but there's certainly 2 isotropic lines defined over C. So it's really, this divisor is not contained in the part that we remove. If we consider the part. Okay, great. And then for D greater 0, some integer, we'll define the divisor delta of D, which is just the sum over all B in R0. Again, I take the trace 0 elements in R. So this is a Z lattice in my quadratic space V up to the action of a star, this delta V, and I want to take all the vectors of length D. So this will define me divisor on H modulo this arithmetic subgroup, so it will define me divisor on X. You can actually check that it really is defined over Q, which is not really important for those, but kind of is. Okay, then let me state one formulation of the theorem of Gross-Kohnen-Zagier. So in the case of the split quaternion algebra, so the modular curve by Gross-Kohnen-Zagier, and certainly in the more general case, it was proven by Borchers, and in fact, Borchers has proven a much more general statement about higher dimensional orthogonal Shimura varieties. So this was late 80s, this was middle of 90s, I guess. So you can consider the formal power series of these divisors somehow. And here by this, I mean, I take the classes in the Picard group of X. So I take the classes of these divisors in the Picard group of X, I take the formal power series, and this is a modular form of rate.
I notice you've started your sum at D equals 0.
Yes, I will make a remark on that. Okay. So in the modular form case, you really get a cusp form, because I take the open modular curve in that case, and somehow I get rid of it. But what you really want to do is first remark what you can do. So what you somehow this is a class of so on this space of isotropic lines, you of course have the tautological bundle. So over every point in here, you just take the elements in this line. The logical bundle. And you can restrict it to this H, and I mean an invariant bundle for the action of our arithmetic group. So it descends to a bundle on this quotient, and that's what you take. You can also say this is, yes, in this case, this is same as a two-dimensional sheet. Or it's dual. I'm always confused which one is the right one, but one of two. But that's like what you generally have to do also in the higher dimensional case. Okay, so that's the first remark. The second remark is there is an interesting property. So if B divides the discriminant of B, then note we're taking square-free level, by which I mean if I take P dividing the discriminant, I take maximal level at that P. Then you have all the vectors in R0 of length D. Well, you can just multiply such a vector with P, and you certainly get a vector, well, that's always true, vector of length P squared times D. You have always this map, but because your quaternion algebra is verified at P, you can easily check that this is the bijection. Which you can just check somehow locally. And so let's do it right. What this implies, of course, is that I use P squared of G equal to G. So your modular form will certainly be ordinary. And this will be used later on. Okay. I mean, just because already this implies this delta D is actually equal as divided to delta D squared. Of course, if you change B by some multiplication with P, you don't change the divisor here. This did. Okay. And so the aim is to give a new proof in case somehow the discriminant of B is not equal to 1 by using p-adic uniformization. X and P that divides the discriminant plus families of theta series, so p-adic families of theta series. With yeah, right. Okay, so and for that, do a little switch. So I fix some new quaternion algebra B, curly B, such that the discriminant of new curly B, the discriminant B is before divided by P, and so naturally B has to be definite. So at P at infinity, I switch the invariant, and at all the other primes keep the same. B. And so I can also look now at curly V, which is just the element of trace 0 in B together with a quadratic form given by the norm. Now this has signature when it's definite, so this has signature 3, 0. So really these theta series I'm mentioning here is really like theta series, so classical theta series attached to a positive definite lattice. Okay. Of course, that's good. So we should be on board. Of course, we have the corresponding conic attached to this new V. as a V acting. But now because V over QP is isomorphic to N 2 by 2 QP to X equals to 0 matrices. So what I get is an isomorphism of a bit of curly V. My conic attached to this new quadratic space at QP is isomorphic to Q1 over QP with exactly the same map. And so I want to consider now the p-adic upper half plane, so taking this conic attached to my new quadratic space, look at the CP value points and subtract the QP value points. And so this is for the purpose of my talk, I just consider this as a rigid analytic space over CP, although it clearly has a QP structure. And I can also pick somehow some additional data. So I pick some curly R, which curly B, and now this is the 1 over P order that somehow corresponds to my R. So if you take an isomorphism of a B localized at some prime away from P with this curly B, then I want that this order matches this. It's totally match. Then there is the theorem of Gross-Kohnen-Zagier, and then given maybe a more conceptual tool like Infeld, that tells you if you start with a Shimura curve I've defined before, X coming from the non-curly quaternion algebra as before, and somehow take the CP value points and consider this maybe base change to P and consider this as a rigid analytic variety. Then this is isomorphic to or HP modulo. Now you take this curly R 1, but this is the elements of norm, elements of reduced norm 1. Okay, so this is the theoretic uniformization theorem. And you can now also compare this Hegner divisors I defined before to divisors defined purely in terms of the p-adic uniformization. Let's go to the next step. And well, luckily everything is still on the board. So you do exactly the same. So you take a V in our curly V. Well, this condition just means V is non-zero now. That's the next condition, and look at the same kind of thing, but now in HP. But this now consists of 2 or no points. So it could be that the divisor, this delta V, is really supported at the boundary of the p-adic upper half plane. But now I can still define this delta D. Now I have this curly R0, curly R1. And this will be a divisor on HP cross. And let me call this R1 gamma. So this will be a divisor on X via the Gehrmann-Greenfeld uniformization theorem. So you're just doing exactly the same thing. And then for the first proposition you want to prove, I mean, it's maybe bad that I've given the two things the same name, but somehow the proposition as the old divisor, the new divisor. Where by old, I mean the one defined by the complex uniformization, and the new one is the one defined by p-adic uniformization. And so how do you somehow get us proof really. Yes. So the new one, remember that this is a Z1 over P order. So multiplication with P is inverted, I mean, given bijection from R0 to just R0. So this new divisor is by definition just so R equals the ones where you multiply D with P squared by definition. Okay, so that's good. So it's enough to assume either that P doesn't divide D or that P exactly divides D. And then you can look in one of the first papers of Bertolini and Damon, where they consider like type of p-adic Gross-Zagier formulas and see that they actually prove this equality there, and Longo has done this in the verified case. But basically, what you do, you can, by choosing some letters at P, you can always assume that somehow you have a optimal embedding in the sense Harvard just told us, and then do this by hand by using the moduli problem. Well,
No H, I think.
what?
No H in Longo.
Ah, oh,
You're confusing it with Longo.
Longi, yeah, no, it's Longo. Sorry. Okay. Okay, so now we've translated our problem into a purely p-adic one. So there is no Archimedean component anywhere. So now, somehow, what are the steps of the proof? Are there any questions up until this point? So now I've more or less stated what I want to prove. I have this new kind of Higner divisors, which in fact agree with the old kind of Higner divisors, and I want to show that the generating series in the Picard group is a modular form of weight 3/2.
So can I just check something? You said there are cases where the p-adic divisor consists of no points at all.
Yeah.
Does that mean that the corresponding divisor in the complex series has to be trivial?
Yeah. So the thing is, in the complex world, our quaternion algebra was ramified at P, which means that if you have a Higner point, somehow P must be inert or ramified in that quadratic extension. But of course, now we have you can embed quadratic fields into our quaternion algebra, a new one that are split at P. And this we want to exclude somehow. This is why you go to
So not that you lose new points.
No. I mean, it's consistent somehow. You lose the same points on both sides.
You have new D, but they contribute no points.
Yes. Right. Which is, I mean, actually to that point, I will come back later. Because there is an interesting phenomenon and we don't know what it means. So, but anyway, let me go to the steps of the proof. So step one, which is actually quite fun calculation, but I won't say much on that. So the first thing you might want to do is you look at the degree of G. So you have this generating series in the Picard group, just hit everything, every coefficient with degree mapped to that. You want to show that this is modular, and you can actually write down explicitly what this is. This is a P stabilization of a genus theta series attached to, you have your R0 and you intersect it with the L, and your L is in VQP, the unimodular VP lattice. So you start with the Z lattice, look at the usual theta series and sum over all the theta series in that given genus. That gives you an Eisenstein series. And then you already know that you get an Eisenstein series of level away from P, but we already know that whatever we get is like invariant under UP squared. So you better take a P stabilization, and it turns out that that thing is already this degree level. And you can just do this by hand. But that the zeroth coefficient is exactly the right thing is like a bit tricky, but other than that, it's easy. And also this p stabilization luckily kills all these extra terms for these d's that are not allowed. So there's somehow it's a very lucky calculation in a way. Anyway, you already know what the degree is here by work of Kudlow, maybe Kudlow-Rappaport already. I mean, you certainly know that it has to be an Eisenstein series, and they also give a specific formula for that as a genus theta or legal by theta series, but now for this other quadratic space. And via some magic principle for theta series for quadratic spaces, you can see that these things. So it all matches up with what we already know. Okay, but this is somehow maybe the easiest step.
You said it again. So you're saying that deck G is an Eisenstein series?
Yeah.
But isn't the Eisenstein series an average of the genus theta series?
No, what I mean by genus theta series is really averaging over all theta series in the G.
Ah, okay. But then, okay. It's not a formal from what you said that it's an Eisenstein series. And
No, I mean, you don't know yet that it's, I mean, if you could use the Archimedean uniformization, get a formula there, you know, it's an Eisenstein series, but this is like a new proof of the fact that you can,
Okay.
which is somehow just combinatorial. Yeah, of course, what's lurking in the background here that you use somehow the reduction map to the Boer-Titz tree and then use like combinatorics, but know that for now. So what's the step 2? Well, you have the PK group already know that somehow taking the degree part, this is the modular form, and you have the Hecker algebra of somehow SOV acting here, and somehow again this is Eisenstein, but now for this Hecker action, which is something different than, and this is Caspidel. So this is Eisenstein. This is Caspidel. So by hitting so TG is somehow we can hit G with an appropriate Hecker operator. That kills the degree part, but is acts injectively on the Jacobian. And it's now enough to consider this TG. Okay. And now using really that we have this p-adic uniformization, because the p-adic uniformization also by, I guess the theorem that goes back to Mann and Drinfeld gives you a p-adic uniformization of the Jacobian. So are we using p-adic uniformization of the Jacobian?
So don't you lose some integral information?
But
I mean, it's this thing will be a direct sum.
but I want to show that it's a modular form, by which I mean, like if you take any homomorphism to C, then what you get. So I lose all. I mean, yeah.
So you're working modulo torsion.
Right. Yeah. Okay. And probably a lot of things I'm writing down now may be wrong, but just tender everything with Q and hopefully it's correct. So, but you have your usual Abel Jacobi map from divisors of degree 0 on X, which I always write as HP modulo gamma to your Jacobian of X. And actually, this space, the Jacobian has also an uniformization, namely you take the homomorphisms of your group gamma, which you uniformize into VP star. You could also take the abelianization, it's the same thing. And well, if I take the level small enough, then up to 2 torsions, this is a free group of genus G, where G is the genus of your curve. So you get this map like this. So you have to mod out some lattice to get the Jacobian. And you can explicitly write down this Abel Jacobi map, but what's even better, we define somehow a subspace of the space of degree 0 divisors, which like strong degree 0, that actually map into this space. So some kind of strong degree 0 condition, which basically means if you take a vertex in the Boas-Titz tree, you look at the star around that vertex, look at the corresponding pre-image in HP mod gamma, then it's of degree 0 on that thing. So you somehow cut your projective curve into affinoid things, and you want on all of these things that it's of degree 0. And how does this map go? So it's very explicit. So you start with some D divisor of degree 0 on HP mod gamma. Then you can just take a lift of that thing to a divisor on HP. So this again a finite divisor. Okay. Of course, there are a lot of choices that you can do. And then you consider f the hat, which is a rational function on P1 or on our conic, which is isomorphic to P1 with divisor with the hat. Again, there are choices involved by this unique up to a constant. So what you do then is, so I want to produce an element in Hom gamma to CP star. So I just take a gamma in gamma, and just sum that in HP that's somehow not in the gamma translate of this divisor. Then somehow I can consider this function as z divided by this function at gamma z. So this is independent of the choice of my rational function. This kills this constant. And now I want that this thing descends to the quotient. So what I just do is I take our sigma and gamma, take this product. Of course, you have to check that this thing converges and so on and so on. But this, well, you can look at this thing. Well, but it really depends on your choice of this lift. And in fact, the thing you have to mod out is exactly the thing you have to mod out to make this independent of the choice of the lift. But for D, this divisors of strong degree 0 does not depend on this D hat if this D hat is somehow good. By which I mean, again, this lift is again of strong degree 0. So, and because it doesn't depend, you really get it. You can check that this is a defines a homomorphism, and this is homomorphism, and so on and so on. So that's one step. So now what you can do is you start with this TG, which is it's a maybe a something in here, but you can like now by choosing appropriate Heck operators, you can really assume that these divisors of strong degree 0. So somehow you can find a lift of that, which lives in this form gamma CP star. So you can check like what are the lifting obstructions or what obstructions to get something of strong degree 0. And it turns out that again, I mean, this is somehow a Hecker module, and it's somehow it factors over the Hecker algebra where P is not in the level. And on the Jacobian, it's not only cuspidal, it's like all P new forms. So you can again hit it with a Hecker operator which is injective on the Jacobian, but you kill this additional degree 0 components. You get a lift here. But that, what can you do? Well, you can just evaluate it at lambda, at gamma, get something in here, and then the p-adic logarithm to get something here. Somehow, our main calculation when now the p-adic families of theta series comes in is computing what happens here. And I call this maybe log gamma of TG. Because you really should see this as you choose a specific differential form of your Jacobian and consider some other logarithm corresponding to that. So anyway, so and you notice that this is really an explicit form. And here you have when before you had here this product formula, you take a logarithm, so you get an infinite sum that you can sort of explicitly compute. Now, finally, step 3, which is the families of theta series. These theta series. So, I mean, you start with your gamma and you want it to be non-torsion. Your level is small enough, gamma shouldn't be 1 or -1. It's like the only conditions. Anyway, evaluating a torsion element would give you something torsion, and then it wouldn't matter for the state. So these are really the ones you want to consider. And what you then get, so this is a hyperbolic element. What this gives you is a sequence of unimodular p lattices T such that sequence then should call it Li. This Li and Li plus 1 are p neighbors, by which Kneser p neighbors, by which I mean the intersection of those is of index p in both of them. And gamma of Li is equal to Li plus k. So, and the sequence is unique with these properties, and they are all different. All different with backtracking. And how you get these? Well, you can realize the Bourdieu tree as the tree where the vertices are unimodular lattices, and two vertices are connected if they are p neighbors. And then such an hyperbolic element has somehow, it means that it has, well, two fixed points on P1 QP, or the CV QP, so at the boundary of the Bourdieu tree, and you just take the geodesic, the infinite geodesic from the one point to the other. This is how you get this thing.
So
And
what's K?
what?
What's K?
Something. Or some big scale. I mean, your gamma shifts somehow this geodesic around in one direction by some fixed distance, but
And can you take any K?
no. I mean, it must be even because I start with something. All elements have reduced norm 1, so they shift at least by 2. But in distance, I'm not sure like how what case can occur. If you make your level smaller and smaller, somehow the case must get bigger because your tree somehow gets larger. So the Bourdieu tree modulo gamma gets larger. Okay. So, and to rephrase what it means to be p neighbors, so your L naught, it really W plus, W minus, and this is your hyperbolic plane. Right, some U. So hyperbolic plane means these two are isotropic, and W plus times W minus is 1. So it's of this form, and these LIs are always of the form the same U, same lattice way from that, and you take p to the I W plus p to the minus I W minus. So these are exactly the lattices you get. And let's call this maybe WI plus WI minus. So it's very explicit how these things look. And now I make a theta series out of that. So what?
Just for clarification, your goal now is to compute log.
Yeah, log gamma of this TG.
In terms of theta.
Yeah. And now I'm going to write down the theta series or that. So what can I do? Well, I start all the vectors in this R naught intersected L, the length D, Q to the B. So that's your usual theta series attached to this definite quadratic lattice. But now, and let's take Li here. Well, I have this for every Li. But I can now pair this vector with V to some K. So this thing is a modular form, classical modular form of weight 3/2 plus K.
Yeah, Q to the D.
Q to the Q of V. Sorry. I want to write down the whole theta series, specific coefficients. Yeah, sorry. And I want to put this in the p-adic family. I mean, it already looks very easy to put this in. Maybe there's a plus and minus option here as well. And I just want to say I take those V such that paired with this isotropic vector, I get something in CP star. And you can check this as an open condition, so it's again a theta series, a classical theta series. Great. But now this thing varies in a p-adic family just because, well, taking something to the power varies in a p-adic family. Great. So this is more or less after p-adic Eisenstein series, the second easiest example of a family of modular forms, I guess. The only problem maybe is that it's of half integral weight, but you could play the same game for other quadratic spaces as well. But now we're doing something fun. I take that thing minus the same thing. Just write it like that. I'm sorry, but this just means I take the one thing minus the other thing. And then I take the sum from 0 to k minus 1. So of all these lattices that show up here. Somehow the lattice Lk is equivalent to the lattice L0.
They're not the same case.
Ah, ooh. Yes. That's it. Thank you. Okay. And so now this is really like a p-adic family of Euler forms, great 3/2 plus s. But now the funny thing is, call this maybe theta s. So the crucial lemma is that this, so, and note that these are cuspidal. So whenever you introduce such a harmonic polynomial, what you get is cuspidal. But what happens somehow at s equal to 0, this thing is in fact 0. And the thing that you have to check is that the condition that V is in Li, that BW BI plus and V plus is the same thing as V being intersection of Li and S Li minus 1. When you have this explicit form, how they look like, and let's do the calculation. So
Can I just
Yeah.
ask again how you make the theta s? So you're taking this, the thing in the middle, the p-adic family, and then you're taking it minus itself?
no, I take the thing with a plus part minus the thing with a minus part.
Okay.
I must screw it up. So I would transfer
Okay.
it down and then take the sum over all these lattices up to the action of gamma. When gamma shifts these things around, and I want to take one for every representative. But then you have this kind of description of this additional thing we put here. It really means that it has to be in sorry. B is in L, so B is not in Li intersected. Sorry. B is in Li, but B is not in this section of Li with Li minus 1. So if you put S equal to 0, this term vanishes, and then you have all these kinds of terms, and they all cancel out. You get this equal to 0. This is also again an easy calculation, but somehow the crucial lemma. So what you can do now is look at maybe theta prime, which is just you take d dk of theta, dts, theta and s equal to 0. And this will be, because the thing vanishes at 0, this will be a p-adic modular form of weight 3/2.
Can I just ask what
Yeah.
the definition of a p-adic modular form of half integer weights
Well,
in this
I mean-
argument is?
You can ask, I don't have an answer. I mean, the thing is, pretend this is, I mean, you could just use like Sayre's definition, like only look at weight k-half modular forms and just take limits of that. It's enough for this talk. Yeah, that was a problem. We hope that what I write next would follow from results in the literature, but there is not much literature on weight, half integral weight modular forms or p-adic families of that. So we had to do this somehow from scratch.
The work of Ramsey.
Yeah, but it didn't really give us what we wanted somehow. At the end, we just did it by hand, and maybe that's the moment where the square free level comes in to play.
What you wanted would be like a classicality.
Yeah. I mean, the next thing I want is that you hit this with an ordinary projector, and you want to say that this is like classical. Weight 3/2. Right, but what we do is just, okay, you can also hit the family before with the ordinary projector, they then take this derivative, can take the somehow commute with the ordinary projector. And then we actually use an out result of HIDA that says like the space of ordinary weight 3/2 modular forms somehow under good properties like I mean the dimension doesn't change when you vary the weight, and you have all these results that if you have a family that's like classical at enough points, and it's classical also at the other point, and so on and so on. So it's like using what HIDA has done in the early 90s. Although he hasn't quite done it for kinds of level we are using. So we needed this constancy of dimension result, but for that we just used that in square free level you have like the Shimura correspondence and know it on the integral weight side. So that's where our method is somehow a bit flawed, but just because we don't know enough about these p-adic families of half integral weight, maybe. And I have also the feeling that you should really work with a vector valued modular forms in setting in general, because you have also this Zagier type, Zagier scopa type isomorphisms of like gamma naught of n with arbitrary level S2, modular forms of level weight 2, arbitrary level gamma naught of n is isomorphic to some weight 3/2 modular forms, but with a specific Weyl representation. So you maybe really want to use that. And this Weyl representation really shows up if you want to formulate Gross-Kohnen-Zagier properly. So it's in any case. So somehow our main theorem is that E ord, and you really have to hit the thing with the same hack operator as before, is the log gamma of G. And I mean, this is just an explicit calculation. You have an explicit formula on both sides, and then you just calculate. But this is wrong. You also have to project to the part where UP squared x by 1. And that's a funny thing for half integral weight modular forms. This UP squared equal to 1 or minus 1 exactly detects on which kinds of integers d the Fourier series is supported. So this again gives you the right these that should show up. So, I mean, maybe I'm not saying much this, but I mean, you could also ask, like, what is E ord of D? So this tells you something about Hegner divisors at the boundary. I mean, this is exactly supported at points which should lie in the boundary of the p-adic upper half plane. I don't know really what this is, but it's a modular form. So and quite naturally defined. So maybe it has some arithmetic meaning. We don't know. Okay. So that's for the proof. I want to say for the proof, but now you can ask me, why do you want to reprove a 35 years old result with methods that are 30 years old? I mean, this. Okay, fair point. But you can also apply this to different situations, hopefully. And the first one is maybe still a bit boring, but this Gross-Kohnen-Zagier theorem also holds for Shimura curves over totally real fields. Theorem by Wan, Zhang, and Zhang, but actually the proof is kind of indirect. So what they do is they prove a Gross-Kohnen-Zagier result for higher dimensional orthogonal Shimura varieties, which is somehow easier because like the first term class from the Picard group to H2 with that coefficients is injective in high dimension, and then it's purely a topological statement, and then you have all these results of Kotler-Milson from the 80s, you can use that, and then you somehow embed your Shimura curve in this higher dimensional orthogonal Shimura variety, and somehow have to compute the intersection, and this is quite involved, and in the end you get the formula you want. But it's somehow very roundabout, and here, I mean, basically writing down the same proof should give you this result here directly. but maybe that's not interesting enough. But I should say, like, this result is from maybe 2010, so it's not that old. So we're getting those are the modern results. Second is so Gross-Kohnen-Zagier for star Higner points. So there are these points on local points on elliptic curves, and these local points are attached to real quadratic extensions, and they should be algebraic, but nobody knows how to prove that, I guess. And there are results of Damon-Tornaro and Damon-Wong in the direction that this generating series should also be modular. And if I look at the proofs, I have the feeling that you really should consider using p-adic families of Kuttler-Milson, or rather Funke-Milson theta series. So Funke and Milson have introduced Kuttler-Milson theta series with coefficients, so introducing polynomials like that. And it seems to me like all the formulas they write down is that you really interpolate these Funke-Milson theta series in p-adic family and then do something with that. So, and maybe, and so why do you might care about the Gross-Kohnen-Zagier theorem? So why did Gross-Kohnen-Zagier care about that? They actually prove a little bit more. They prove that this modular form you get, if you restrict it to an elliptic curve corresponding to an capital eigenform, then this generating series is exactly the Shimura lift of that eigenform. And then using multiplicity 1, you get that all the Higner points live in a one-dimensional Q vector space. So this was before Kolyvagin. So you didn't have the result of Kolyvagin that if the Higner point is non-zero, then you know the rank has to be 1. So they showed via their methods that all these Higner points you can construct live in a rank 1 subthing. And you can basically apply the same methods here as soon as you have this result. So you don't know that these Gross-Kohnen-Zagier, that the star Higner points are algebraic, but you can show that they live in a Q vector space of dimension 1 once you have a result like that. And maybe point 3, which is one I'm thinking about most at the moment. There's this theory of eclectic points by Ricky Lefournier, and I worked on this as well. So these are strange points that live in something like you have an elliptic curve over a totally real field. So you have E over F, and this is totally real, and you have a bunch of p-adic primes, P1 and 2 PS. You have multiplicative reduction there, and you construct points in something like change topological space. So you take all the localizations of your elliptic curve, take the CP valued points, and take tensor product. So this is very strange piece, but in here we produce points. And actually, like you can also parameterize this with some U, which is now, I guess, an ideal in F. And you can ask about the generating series of these points. Is this again a modular form? And the answer should be yes. And here you're using Hilbert theta series. And actually there are, when you can cook up a Hilbert theta series in several variables, but you can check that, I mean, somehow 1 for each prime. As soon as you're constantly equal to 0 in one variable, your thing will vanish. So that's like this easy strengthening of this lemma. So somehow only one, somehow there's this ds1 until dsr theta and equal to 0. So this is somehow the unique leading term. All other leading terms vanish. And so you want to relate something like this to to these points. And somehow you can get explicit formulas for both things on both sides, but it gets harder because you have to have this thing maybe with an ordinary projector for every prime, and the calculation just become very messy. We try to see what's going on in the literature where you have 2 primes at the moment. I should say this is a joint project with Michele Forner and Marty Rosell. Here.
Are there any comments or questions?